Hey, welcome. Today, we're going to tear down something you've probably never thought much about: industrial mixers. Now, yeah, they might look like just giant egg beaters, but they are absolute marvels of engineering. They have to work under some seriously extreme conditions where, failure is just not an option. So let's get into how they pull it off.
So get this. Imagine this is your job for the day. The stakes, well, they couldn't be any higher. You're wrestling with massive forces, incredibly dangerous materials, and the constant threat that the whole thing could just fail catastrophically. This, right here, is the core challenge for the engineers who build these amazing machines.
And really, that's what this is all about. We're not talking about just gently stirring some tea. We are talking about controlling a violent, chaotic storm inside a gigantic, sealed-up tank. It is a constant, brutal battle against the laws of physics. Okay, let's start with the absolute basics. At its heart, an industrial mixer is really just an energy conversion machine. It takes electricity from the wall and turns it into very controlled fluid motion. But here's the wild part. Every single watt of energy you put into that system, every bit of it, eventually just becomes heat. The mixing is just the work you get done along the way. Kind of cool, right? So that brings us to our first huge problem. How do you even generate, let alone control, the insane amount of force you need to move, say, thousands of gallons of something super thick and heavy, or even something really reactive? And the real key here isn't just power. It's torque, that raw, twisting force. Think about trying to open a really, really stubborn jar. You don't need to be fast, right? You need that slow, powerful, brute force twist. That's torque. And just like it says here, that one single factor, torque, pretty much dictates the size and strength of almost every other part of the machine. But hold on. Before you even think about applying any of that force, you have a life and death safety problem. In a lot of these plants, the very air you're breathing could basically be a ticking time bomb. One little spark from a standard electric motor, and it could be game over. So, of course, engineers use special explosion-proof motors. And this is not a one-size-fits-all solution, not even close. You can see here, the motor has to be specifically rated for whatever hazard is around. So a motor that's safe for gasoline fumes in Group D might be totally useless, even dangerous, next to the more volatile chemicals in Group C. And then you have combustible dusts like flour or even coal dust. They present a completely different kind of ignition risk. It's incredibly specific. All right, so you've got a safe motor picked out. Now, how do you get that stubborn jar opening torque? Well, the answer is the gearbox, or what's called a gear reducer. It's this brilliant piece of engineering that takes the super fast, low-force spin from the motor and, through a set of gears, transforms it into that slow, powerful, high-torque rotation you need to actually move all that fluid. But, generating the force is really only half the battle. Now you gotta solve an even trickier problem. How do you keep what's inside the tank? And that's way harder than it sounds when you have a giant spinning steel shaft that has to go right through the wall of the vessel. And you can really see the evolution of the technology here. The old school way was a stuffing box. It's basically just rings of this tough, greasy rope packed tight around the shaft. It's simple, it works, but some leakage is literally designed into it. And when you're dealing with hazardous stuff, that's a no-go. Today, the standard is the mechanical seal. It's a high-precision device that gives you a much, much tighter seal. So how does this thing even work? Well, the basic idea is pretty mind-blowing. A mechanical seal uses two incredibly flat, hard rings. We're talking materials like ceramic or carbon, and they're pushed together by a spring. One ring spins with the shaft, the other stays perfectly still. The seal is created in the microscopic gap between them, which is filled with just a super thin layer of the liquid being mixed. It is precision engineering on a whole other level. Okay, so the motor's safe, the tank is sealed up tight. But now we face maybe the most sneaky, dangerous challenge of all, preventing the entire machine from shaking itself to pieces. I mean, just look at what this poor shaft is dealing with. You've got its own weight pulling it down, you have pressure inside the tank pushing up, you have hydraulic forces shoving it sideways, you have the torque trying to twist it, and these powerful bending forces trying to snap it. It's under a constant, multi-directional attack 24/7. To get this, you have to understand a concept called natural frequency. The best analogy is a kid on a swing. A swing has a natural rhythm, right? If you push it at just the right moment, matching its natural frequency, it goes higher and higher with almost no effort. Now, imagine that swing is a 50-foot solid steel shaft. If the mixer's operating speed accidentally matches that shaft's natural frequency, the vibrations just build and build and build until the machine can literally tear itself apart. So designing a shaft becomes this very careful back and forth process. First, the engineers figure out the minimum diameter they need just for basic strength, so it won't break. Then they run the numbers to find that shaft's natural frequency. Is it too close to the mixer's operating speed? If it is, they can't just change the speed. They have to go all the way back to step one, make the shaft thicker and heavier, and then recalculate everything all over again until it's both strong and stable. But here's the thing. Even the most perfectly designed shaft in the world is completely useless if the foundation it's bolted to is weak. The whole structure holding this multi-ton machine has to be ridiculously rigid. On the left here, you see a simple side view, and it looks like the beams are just there to hold the mixer's weight, right? But the overhead view on the right, that tells the real story. Look at all that cross-bracing. That's the secret. Because all those forces are dynamic. They're shaking and twisting. The support structure has to be stiff in every direction, not just up and down. Without that bracing, the whole thing would just wobble itself into failure. And this really brings us to the most important takeaway of all. You can't think of these as a bunch of separate parts. You have to see it as one single, completely integrated system. The motor's job is to provide the raw power. The gearbox converts that power into torque. The seal makes sure everything stays contained. The shaft has to deliver that torque while surviving all the vibration. And the mount holds the whole thing steady. Every single one of these pieces is designed in relation to all the others. If one part fails, the whole system fails. And check out this number. This shows you just how seriously engineers take the violent, dynamic nature of this whole process. When they design the nozzle on the tank where the mixer actually mounts, they don't just calculate for the maximum torque. No way. They multiply it by a safety factor of 2.5, sometimes even more, just to be absolutely sure that structure can handle all those unpredictable forces. So at the end of the day, a successful industrial mixer isn't just a collection of really strong parts. It's a holistic system. It's this complex dance between physics and engineering where every single component, from the type of motor to the thickness of a steel beam, is precisely calculated and balanced against everything else. So the next time you see any kind of manufactured product, the paint on a car, the plastic in your phone, anything, just take a second. What unseen high-stakes world of engineering, just like this, had to exist to make that thing possible? It's a fascinating world hidden just below the surface. Thanks for watching!